So I'm Andrew Schran, engineer at Mysten, and I'm here to talk about native randomness on Sui. This is a new feature we've been working on for all of you, and it's available today on DevNet. So everything I'm talking about you can go play around with right now. So before I dive into the technical details about decentralized randomness, I just wanted to spend a little time talking about why do we want to have randomness on chain in the first place. And there's actually more use cases for it than you might at first imagine. So I'm not going to read out all of the ideas that are on these slides, but here are some just to get you started. So as you might have thought of already from the last presentation, the most obvious use case for randomness on chain is games of chance. Card games, lotteries, raffles, casino games, stuff like that. And we already have other ways to build games of chance. You can already play games of chance. So why do we want to do that on the chain? Savon alluded to one of the big reasons for doing that is because it makes it possible to build a game that does not require the user or the player of the game to trust the operator. So the player can look at the code and then see for themselves that it works exactly as promised and no one's being cheated or misled. Another way you can use randomness is to take a sample, like take a random subset of a larger group. And there's actually a lot of use cases for random sampling, and one domain that comes to mind for me with that is governance. So just to give a few examples, perhaps you have two opposing sides in a dispute, and they don't trust each other. They could use random sampling to select a jury that then arbitrates their case. Or imagine that you have a school, and there's limited spots in the school available for admission. What the school could do is use on-chain randomness to run a verifiable lottery for the spots available for admission into the school. So the entire process is auditable and guarantees fairness. You don't have to worry about someone getting snuck in because they know somebody or anything like that. You can do this all in sort of like a verifiable, trusted way. Randomness lets you easily make random NFTs. That's a use case we expect to see a lot of. NFT that has different levels of rarity that are assigned probabilistically, and then when you open the NFT, you see which one you get. Or you could imagine a more creative example along the same lines. Say that you had a CryptoCat NFT. You could make it possible for two of your CryptoCats to have a kitten, and the kitten could randomly inherit some of the traits of each of the parents, or maybe also have some random sort of mutations. So you can do fun stuff like that with randomness and NFTs. Or you could even imagine using randomness to inject a little bit of fun and excitement into your app. Just to give one example of this, like how about you make a store with double or nothing payments. So every time customers make a purchase, they have a 50% chance that they could win the item for free or else they pay double. So you could get as creative as you want with this. But anyway, so now that we have some ideas for why we want randomness on chain, let's talk about the technical side of it some more. How do we go about implementing decentralized randomness? So in order for randomness on chain to be secure, we need it to have two very important properties. The first is that it's unpredictable, and the second is that it's unbiasable. So when we say unpredictable, what does that mean? It means no one can guess what the randomness will be in advance before we're already using it. And then for randomness to be unbiasable, it means that no party who's involved in generating the randomness can unilaterally affect what randomness actually gets generated. And why is this important? Well, if your randomness were predictable, an attacker could simply simulate what your app is going to do in advance because they can predict what the randomness will be and then front run your transactions, or maybe they only call into your app if they already know from their prediction that the outcome of the call will be favorable to them. Or if the randomness is biasable, they could likewise use that sort of bias in the randomness generation against you to change the outcomes in their favor. So we definitely need our randomness to be both unpredictable and unbiasable if it's going to be secure. And of course, that's the table stakes for security, but it would be nice as well if we can have our randomness be fast and easy to use, have a nice API, perform well, not be too costly. So let's talk about the existing solutions to this problem. There are many existing solutions. And they all have various trade-offs and disadvantages. The simplest idea you might think of is just using an external source of randomness. And that works fine, but it's not really decentralized. It's predictable and biasable to the extent that you don't trust that source of randomness not to collude with other parties or to actually give you random bytes when you ask for them. So there's various decentralized solutions. I listed some here on this slide. I'm not going to go into the details of the sort of cryptographic techniques here in this talk, but some approaches, commit and reveal, or VDF stands for verifiable delay functions. VRFs are verifiable randomness functions. Most of these existing solutions have various trade-offs based on the details of how the approach is implemented. So based on the details of how you implement your VRFs or your commit and reveal scheme or whatever it is, they're often predictable or biasable, or else the techniques that you use to make them not predictable and not biasable either make them work too slowly, like the verifiable delay functions, as you might guess from the delay in the name. We decided are kind of too slow for our use case, or else the implementation that makes it not predictable, not biasable, requires all of the parties to kind of be live and contributing to the randomness, and if one of the parties stops generating randomness, doesn't respond anymore, becomes Byzantine, then the system kind of grinds to a halt. So what we did is we chose a newer approach. It's based on threshold cryptography, a distributed version of VRFs that we think has the best properties for randomness on Sui, and it's better than most of the existing solutions. It meets all of our requirements. It's unpredictable, it's unbiasable, it's fast, and even if up to a third of the validators start misbehaving in some way, a third of validators we often refer to with the letter F, then the system continues to work. So there's a lot of nuance and detail in how our implementation works, but just in a very broad sense, how does our protocol work? There's two phases. The first phase runs at the start of every epoch, so roughly once a day. All of the nodes use a DKG protocol, which stands for distributed key generation, to agree on a key to use for generating randomness. There's a public key that all of the validators know, and then there's a secret key that through some cryptographic magic gets split into shares, and validators all have a share of the secret key proportional to their stake. And then the second phase happens in just continuously throughout the epoch, every time we're generating randomness. Basically, you have a randomness round, which is sort of like one set of steps that at the end generates a set of random bytes. And for each round, basically, the validators all communicate with each other to send signatures on an incrementing counter that increments each round. And once you get F+1, that's more than 1/3 of the shares of signatures on the secret key, then you can use, again, the sort of cryptographic primitives we're using to recombine those signatures into those partial signatures into a full signature, and that full signature we hash then to generate the randomness for that round. Again, there's more sort of intricate cryptographic details you could get into here, but the upshot as far as the properties of the protocol is that you have your DKG that is a little bit slow, but only has to run once per epoch. And then once you're generating randomness, you only actually need to get signatures from more than a third of the other validators to reconstruct the randomness for that round and execute it. So you don't have to get data from all the validators, which makes it pretty fast and resilient. There are existing solutions that use a similar protocol to the one we've implemented natively in Sui. DRAN comes to mind. These are generally oracles that run their own protocol and post data back onto the chain. These work well enough, but they have some caveats. So for example, the oracle will periodically post new randomness data to the chain. So you might think naively, OK, I'm writing an app that needs randomness. I can just look what's the most recent value of randomness that's posted to the chain and then use that in my app. But what's the problem with that? Well, it goes back to the need for the randomness to be unpredictable. If you write your app to use randomness that's already been generated, just take the most recent value that's posted to the chain. Everyone else knows what that value is as well. And so someone could just simulate what your app is going to do based on the randomness that they also already have access to, and then decide whether or not to call into your game or your app, whatever it is, based on what they already know the outcome will be. So they can guarantee that they're always going to win the coin toss or whatever it is. So to fix this, the existing solutions that are using the oracle-based approach require that you split your random operations up into two separate transactions. So first you have to send a transaction that commits your application to a future round of randomness that hasn't been generated yet. And then you wait for DRAND or whatever it is to kind of continuous process and post that future randomness to the chain. So then once it's available, you send a second transaction, and that transaction uses the randomness output that you previously committed to. So as you can maybe tell from the description of this process, it's kind of cumbersome to manage as a developer. It's slower than we want it to be because you have to wait for new randomness to be posted from this external oracle. And to some degree, even if you trust DRAND or whatever the service is, it still requires you to trust external nodes that are not the Sui validators that are already running the Sui network. So it just adds the overhead of an additional sort of trust model to the existing one. So I'm kind of alluding to this by what's, in our view, a little bit deficient about the Oracle-based solutions or the existing solutions, but why do we want native randomness on Sui? By comparison, it's much easier to use. We are able to implement a simple one-step API for you. You don't have to do this commit and then execute two-phase API. You don't have to trust any external oracles. It's still secure, it's unpredictable, unbiasable, and it's much faster because we're not waiting for like a round to come from outside the chain that takes a few seconds. So I wrote here on the slide less than 200 milliseconds typical randomness latency. What this means is if you have a transaction that depends on randomness, based on how fast we're observing in our benchmarks, randomness gets generated. It will take less than 200 additional milliseconds to execute, like once the randomness that it needs becomes available, compared to a transaction that doesn't use randomness. That's at like 95th percentile. So typically it'll be even faster than that, like 100 milliseconds median or something like that. So how did we, if we dive into the details a little bit more, how did we actually implement the native randomness in Sui? The initial way you might imagine doing this, which was at least my initial idea, was to just do what the oracles do, but for you behind the scenes. So we have the two-step process where we commit to a future randomness round, and then later we use that round once it gets generated, and we could do that behind the scenes for you in the validators. We'll hold on to your transaction, defer it, wait for new randomness to become available, and then we just implemented sort of a randomness generator in our consensus layer that periodically sort of posts it back to the Sui chain. And once that randomness is available, then we can no longer need to defer your transaction. We can pop it off the deferral queue and execute it. So that works. We went pretty far down that path of implementing that. But there are some problems with it. It's still a little bit slow. Even if we're holding your transactions automatically to wait for that new randomness, we have to wait. Basically, you can't use randomness for any, if there's a randomness round sort of running continuously in consensus, it will be in a state where some of the partial signatures for that randomness have been revealed, but not all of them. And if any of the randomness for a round that's already in progress has been revealed, you can't use it, or else your randomness might be predictable. So basically, you have to wait for the current round to finish, then the next one to start, and the next one to finish before you can then use that value of randomness for your transaction. And that's how we make sure no information is available about the randomness you're using until it's too late to do anything. But that means it's still kind of slow. You have to wait for, on average, 1.5 rounds of this periodic randomness generation process to complete before you can then take your deferred transaction and execute it. So it's a little bit slower than we want. More importantly, even if we do this whole deferral thing, there are some security concerns with this approach. Basically, the validators who are running the randomness generation will know the next value of randomness a little bit before the order of transactions that comes out of consensus is totally fixed because of this deferral process we're doing. So it means if you had a malicious validator, they could potentially do some kind of front-running attacks against your application where maybe they like decide, okay, I know the next randomness and this transaction should be in the block, but it's not going to go my way that I want it to, so I'm just going to like not include it in the next block, maybe wait for it to be in the following one, and then you have a malicious validator that's able to bias the results of your randomness application. So we went down this path until we realized that basically mitigating this sort of front-running attack, MEV attack, whatever you want to call it, actually gets quite complicated. Changed gears and ended up with what we're now launching as the approach we're taking for native randomness on Sui, which is we're going to integrate the randomness generation directly onto the Sui side. Instead of just doing the same thing that the external approach does for you internally, we have random bytes. Basically, backing up a little bit, every time we get a batch of ordered transactions from consensus, we're not doing deferral anymore, so that means by that point the execution order of the transactions is fixed and can't be changed anymore. And only then at that point do we start generating a new round of randomness for the transactions in that commit. So instead of having it continuously run in the background, we now generate a round of randomness for every consensus commit. And we use a new protocol that we created for that runs out of band with consensus just between the Sui validators. So what that means is a front-running attack is impossible because you don't start revealing randomness for the transactions that are in a commit until after the order is fixed and nothing can be changed about it. So by integrating the randomness generation into the Sui side, instead of sort of doing it as this continuous background processing consensus, we can provide a one-step solution that's totally secure, that we don't have to defer your transactions, that use randomness until some future round is generated. And as a bonus, that makes it really fast compared to existing solutions. So The Oracle-based approach we discussed can take 5 seconds or more for the whole process of splitting it into 2 transactions, waiting for the next round to be generated, then executing the second transaction. And again, as I mentioned before, for this, it's more like 100, 200 milliseconds extra latency compared to a transaction that doesn't use randomness. So how do you actually use our new randomness feature in your apps? The API is super simple. I'm not going to get into a ton of detail about it in this talk. Frankly, there isn't that much more detail that I'm going to be talking about. It works kind of like you would access randomness in a non-Web3 application. We have this random system object that you include as an argument to your function. And then you can call new generator, pass in the random system object, and it will use that to create a pseudo-random number generator. And then you call functions on that generator to get random bytes, random integers, random numbers in a specified range. Really easy to use. I want to talk briefly about security. There are, because we're still in Web3, there are a few things you need to do to make sure that your app is using randomness in a secure way. So the first example I want to talk about is a category of attacks we call composition attacks. So basically, imagine if you had, naively you made a function that is like some game that you're playing with your user. They pay some Sui to play the game, and then if the user wins, you return a coin, and if they lose, you return nothing. So you have this return value that's an option on a coin. And if you made this a public function that anyone can call, why is that bad? Well, what could happen is someone creates their own function that calls your function and then tries to extract the value of the option that gets returned by your function. If the user won, then that extract call succeeds and they get the coin back. If the user lost, it fails, and then the transaction aborts, gets rolled back, and it's as if they never sent it. So therefore, they can guarantee that they always win because only the ones that win will go through. So we call that a composition attack. Basically, you don't want to let someone else compose your randomness function into their own smart contract code. So the solution for this one is pretty simple. If you have a randomness using function, don't make it public. Make it an entry function so you can call it directly in a transaction, but you can't call it from, you don't let other people call it from their own smart contract code. And this is something that will be we help you along with stuff like this. I'm going through details about these sort of security concerns in the talk, but you don't have to worry too much that like, oh, this is a minefield. How do I write a secure app? Because we'll have a compiler warning, or else the system will forbid things for the most part that are insecure. So here's one more example. What if you wrote a function like this? So you have your game that the user can play. They give you a coin as payment again, and then you make your random number generator, and this is basically just a coin flip game. You generate a Boolean. So if the Boolean is true, the user wins. If it's false, the user loses. And then you run some code, and the code is different if the user wins than if the user loses. So what happens here is if the code that runs when the user loses is more expensive to run, it costs more gas than the code that runs when the user wins, what a attacker can do is they can call into your function with a gas limit set so that if the user wins, there's enough gas, the transaction succeeds, and then the user collects their winnings. And if the user loses, your function tries to do more stuff, runs out of gas, and then the transaction gets aborted. And again, we're in a situation where we have selective aborts, and the user can call your function in a way where they never lose. So to prevent gas-based attacks, here I wrote on the slide, basically we call it the happy path and the unhappy path. You have to make sure to not use more gas in the unhappy path than in the happy path so that users can't call your function with just enough gas to only ever be happy from their perspective, but unhappy from your perspective, I guess. Don't worry too much about the specifics again. We help you along pretty well with restrictions, and this is built into the system with compiler warnings and other stuff to help you avoid these issues. And we wrote a very nice developer guide, which is available at this link. And that has all of the details about the various nuances here. So just to recap, Sui native randomness, it's available today in DevNet, coming soon to testnet, and we have a solution here that I'm pretty proud of. We think it's faster, easier to use than existing solutions, and we are really excited to see what all of you can start building with it. So just to show you what this can look like, I'd like to invite now my friend Jian Lu up, and he's going to give us a quick demo. You want this, or do you want to use the lecture?
Hello, everyone. My name's Jian Lu. I used to be the Mysten smart contract engineer, and I have since left Mysten to start a software consultancy firm to build fun games on Sui. So Double Up Casino is one of our clients that we have worked with, and we built their Plinko game for them. And this version of the Plinko is using the DevNet randomness, which is much faster and more interesting. Here, let me connect and I'll just show you guys. Ignore the 2.1 million DevNet tokens, but I also used to be the engineer on Faucet. So what's really neat about the randomness is that we actually see, I've already built the smart contract, it already executes, and we can see that we get some type of response and balance changes already. We've given the recommendation to the wallet UI team to probably show something else, because this uses the previous randomness seed to execute the transaction. So if we executed this in the last round, we would have won like 52 Sui. But when we execute this for a future round, which takes about 200 milliseconds, we can drop the balls and then see what actually happens. So if I lose money here, I'll blame Andrew. So we can see that we made something like 26 Sui here, or 27 Sui, and not the 52 Sui. The trade-offs of this are pretty interesting. I can show you guys what the old version of randomness that we use is. And you can really see that there is a significant lag in user experience. This new version of randomness is going to empower so many more apps on Sui. I think it goes beyond just the simple games. You can really do things like a full lottery that's going to be, I should switch to testnet. So this is the old version basically here, and we can see that it's testnet related, and you can see that there was like almost a 2-second lag because we're waiting for another backend to run and sign a transaction to generate the second version of randomness. Yeah, basically this will empower a lot more apps like lotteries, raffles. You don't have to rely on a third-party oracle. The stuff comes much faster. Everything is native on Sui. It'll empower a lot more things and applications here. Please participate in the Sui Overflow Hackathon. There is a randomness track, and I'm advertising for a foundation here. Yeah, thank you guys.